Right, so we're gonna start with 7.8 today, and we're gonna do some applications of exponential and logarithmic function. So the exponential growth and decay formula for, continuous rate of growth, is this equation, y equals y naught e to the kt. Okay, what does that remind you of? This is very similar to a equals p e to the rt. When we had that, this was the final amount, this was the initial amount. You have a rate times the time. Here too, it's exactly the same. Y is the final amount. And in math, right, it's always, what do you call it? Like the most concise form, so you can avoid using too many letters, is if you have one letter, right, for final amount, then you can take the same letter with a subscript 0 and use that for initial amount. So y is the final amount. Y naught, that's how we read that, is the initial amount. K is the rate of continuous growth. So in math, when we have exponential growth, right? And remember the formula, y equals, remember like this one, a 1 plus r to the power of t, right? We use r for rate. But then when it's a continuous rate of growth, when you hear the word continuous, then we use the symbol k, and then that's how we know that that's a continuous rate of growth. Okay, so if k is continuous growth rate, then k will be positive, and that's how the equation will look. If it's a decay, then k is negative, all right? Okay, one place that this is used very widely is carbon dating. You guys know what carbon dating is? Okay, so every living organism, right, contains carbon, right, in our bodies. Okay, so once a living organism has died, the carbon-14, that's an isotope of carbon, the carbon-14 in their body begins to decay. And then when they find a fossil, they look at how much carbon-14 is remaining in there, and that's how they can figure out how long ago that organism has died. Okay, so that's called carbon dating. Okay, and this depends on the half-life of carbon-14. So how many of us have heard the word half-life before? What half-life is the following. Suppose you have this much of a substance, okay? And suppose this is a substance that decays on its own. Suppose in 50 years, half of this decays and half of it remains. We say the half-life is 50 years. So now 50 years have passed and half of it decays. 50 more years and half of that will have decayed. In another 50 years, half of that will have decayed. That's what half-life is. So half-life is a time unit. Half-life is in years, right? So half-life is the time it takes for half of something to decay, all right? So carbon-14 has a half-life of 5,730 years. It means if I have 100 grams of something in 570, whatever, in that many years, how much of it will remain? 50 grams, okay? So carbon-14 has a half-life of that many years. We need to find the value of k. You always start with this equation for half-life, always. So take a look. The initial amount is y naught, okay? So if we're talking about half-life, the final amount is always going to be half of the initial amount, half y naught. E to the power of k times 5,730 years. So what this equation tells me is 5,730 years have passed. The initial amount was y naught, and now there is half y naught. This is how a half-life equation is always going to look. So now we're just going to solve this for k. We get rid of the y naughts. So I have half is equal to e to the 5730k. I take ln of both sides. So I get ln of a half is 5730k. So k is ln of a half over 5,730. Okay, go ahead and take out your calculators and plug this in for me, please. Is it E? It's a scientific notation. So what it is negative 0.0001297. Okay. So that's K. All right. And do you see how K is negative? Because this is decaying. This is exponential decay. All right. So now we need to write an equation. Yep.
How do we get it like out of that form?
You have to change the float setting. So give me okay. So go to your if you're in Scratchpad, go to Scratchpad. So to write the equation, it's going to be y equals y naught e to the negative 0.0001297 t. Okay, this is where many of us are like forgetting, that you have to write the equation. And then when you write the equation, you have to make sure y is in terms of a variable and t is in terms of a variable. And then, y naught is the initial amount, so just put y naught for now. Okay, if a specimen contains 100 grams of carbon-14 today, how much will be left after 200 years? So here it's going to be y equals 100 e to the k times how much? 200. All right? And when you plug that into your calculator, you should get 97.6097 grams. Okay? And I will have specified on a quiz or test how many decimal points to go into. All right? So look at that. The half-life is 5,700 years. So if I have 100 grams, 200 years later, all I've lost is like 2.4 grams. All right? That's how slow carbon-14 is to decay. All right? Okay. And then different isotopes have different decay rates. So for example, the half-life of sodium-22 is 2.6 years, much more quickly, right? So determine the K value and the equation of decay. All right, so you can, if you are comfortable with this, you can skip to this step right here. Okay? You can always skip to that step. So you can say from the beginning, since this is half-life, half is equal to e to the 2.6 t. Okay? You can always skip to that step because it's always going to be half y naught equals y naught, blah, 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 and the y naughts are going to go away. Okay? So now you take ln of both sides. Ln of a half is ln of e to the 2.6 t. Ln of a half is 2.6 t. Yep.
When we take ln and d, can we just skip to the...
Yes. Yep. So then t is ln of 1/2 over 2.6. Yeah. Oh, sorry, it's all K. Sorry, it's all K. Oh my gosh, sorry. Okay, so this will be, so K is going to be negative 0.26659. Is that the final answer? No. The equation is y equals y naught e to the negative 0.26659 T. All right? Yeah. Okay, so I will definitely specify, but we don't, I don't want you to go to like less than 4 decimal places, okay? All right.
Don't we know what T is?
No. You know what T is for half-life. So you know what T is for one cycle to happen. But if you want the equation, you have to have Y and T in there as variables so that you're able to plug in T for like any other problem. Okay? All right. So a geologist is examining a meteorite and they estimate that it contains about 10% as much sodium-22 as it would have when it reached the Earth's surface. How long ago did the meteorite reach Earth? Okay, so the equation y equals y naught e to the kt. Okay, if it contains 10%, right now it has 0.1 y naught, and initially it had y naught. E to the, what is k? Negative 0.26659 t. So this goes away. We take ln of both sides, so I get ln of 0.1 is negative 0.26659 t. Divide by t, and I get ln of 0.1. Yep. I don't know what I said, but we're dividing by this number. Okay? So that's what we have.
What, like, how does, why is the point negative 0.26659, like, what is that?
That was the K that we found in the first problem.
Yeah, but like, what is that?
That's the growth rate. That's the decay rate in this case. So this equation, y equals y naught e to the kt, right? Final amount, initial amount, rate, and time. Right? So that's the rate at which the sodium is decaying.
Then how does that relate to this?
Huh?
Like, how does that relate to
Because
this?
like A and B were, this is part of the same problem, A and B.
Yeah, but how, like, I don't get how, if there's no, like, decay in this.
No, there is, because a geologist, okay, so this is part B of this one, right? We have sodium decaying. So now a geologist has a meteorite. It now has 10% of the sodium that it had when it reached the Earth's surface. So a meteorite hit Earth, it has some amount of sodium in it. Now it only has 10% because it was decaying at this rate. So we want to know how long ago it hit the Earth's surface. Okay? So this is going to be 8.6370. So it's about 8.637 years. I plugged this into my calculator. Okay, speaking of which, if you don't have your calculator on your desk, this is a good time to do that. Okay.
Oh, is that 8?
Mm-hmm. Okay, so in 2007, the population of China was 1.32 billion. In 2000, it was 1.26 billion, right? So now it's growing. Determine the value of K for China's population and the equation of growth. So again, the final amount is 1.32. When it's in terms of billions or millions like this, please don't put the zeros, right? Just put the 1.32 equals 1.26 e to the k times t. How much is t in this case? 7. Taking, first we have to divide, right? 1.32 over 1.26 is e to the 7k. Taking the ln of both sides, ln of that fraction is 7k. So k is ln of 1.32 over 1.26 divided by 7. Okay. So, all right, Todd, tell me how much k is. So 0.006645. The more decimal places you go to, the better, because then there's less rounding error. Okay, so for the equation, take a look. Let's go to the previous one, okay? Let's go to the previous two, actually. In the first one, when we had carbon 14, we had the value of k, and then we had to write the equation. We didn't have an initial amount. Is everybody listening? Stop writing for a minute, listen to me. We didn't have an initial amount to go on here. So we put y equals y naught, blah, 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 right? Same thing here. When at the point where we had to write the equation, we didn't have an initial amount to go with. Here, however, we're given an initial amount from the get-go. So, Todd, have a seat for a minute. So when we do this, right, you're going to put in the initial amount because you are given it, and then e to the power of 0.006. Oh, sorry. 45 t. Okay? All right. Okay. When will China's population reach 1.5 billion? Okay, so by the way, all right, well, okay, so when will China's population reach 1.5 billion? So now this is the final amount. So we're going to say 1.5 equals 1.26 e to the point, the k times t, divide by 1.26 is equal to e to that number, taking ln of both sides, okay, divide by k, so we get t is 26.2 years. Now, the question is asking when will it reach 1.5 billion, not after how many years. So you have to give the exact date. So 26 years after 2000, that's in the year 2026. Okay? All right. One other thing I want to talk about is on the calculator, right? So initially it was 2000, right? In 2000 it was 1.26 billion. Now, if you use the 1.32 and started from 2007, it'll still work. Your answer will just be 7 years less. Okay, so like instead of 20, it will still work. Instead of 26, you'll just get 19.2 years. But then you have to go forward from 2007. Does that make sense? Okay, so take a look. One thing I want to talk about is this. I want to remind you to use the, like the answer whenever you can. So let's take a look at this one. Let's find k here. Okay, so how did we find k? It was ln of 1.32 over 1.26 divided by 7, right? Whoops. Oh, the division sign. Okay, there we go. All All right, and then we wrote down that it's, whatever, 0.006645, blah, 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 okay? And now here, okay, now here I want to do my final answer, right? So I have ln, right, for this part at the very, very bottom here, okay? So I want to do ln of 1.5 over 1.26, and I want to divide this by the k. Okay, so again, there are two ways you can do it. One way is you can just go up to wherever that number was, highlight it, press enter, and then just put in the whole thing instead of typing it again. I really suggest you do this, and then, you get that answer. So, and then, okay, so now here's why that's a better way than like doing that. So suppose you want to do like some other number divided by the k. Where was the k? It was like several steps ago, right? If you do second answer, I'm sorry, if you do control answer, it'll just give you the previous answer of 26. But suppose that's not what you want. What you want is, is this rate that you did several steps ago. This method lets you go up and choose whichever step in like the whole like repertoire that you have. And then you just you just press enter, and there you go. All right, so really get used to doing that. If you do second answer, you just get like the one right above. You can even, if you press the up button, you can even go back and let's say bring back an operation that you put, and then it'll give it to you in editable form, and you can just go in there and edit. Okay, so that like I use that a lot. I always like go up, 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 and then select. Okay, so that's the lesson for today.